Okay, well, today we'll talk about the Pascal triangle. I'm George Ganser, because I know that back there. So, quick little history and origin. The Pascal triangle is named after the French mathematician Blaise Pascal. Although the triangle is named after Pascal, he was not the first to recognize the triangle pattern. References to the portions of the triangle were seen in the 11th century and ought to have, or thought to have been brought over by the way of Arabia and China. So within the there's a lot of themes within the Pascal triangle. The more you look at it, the more you can discover. So one of them is the binomial coefficients, which is used a lot in statistics. So in order to find how many combinations you can get out of a set of things, you can use the formula n over k and n factorial over k factorial times n minus k. Yeah. So you can use that, which is used a lot in statistics, but you can also use you can go and say, okay, well, if you want to find out how many, you can pick 3 objects from a set of 5. You go to the triangle. So the top row is the 0 row, first row, second row, fifth, third. So 1, 2, 3, 4, 5, and then you go 3 over. So 1, 2, 3. So you have 10 different ways to pick 3 different objects from a set of 5, and that's shown here from 5 choose 3. So that's how you can see the binomial coefficients within the triangle. And then here's a proof. So here we're just proving that n plus k over 1, or n plus 1 over k equals n over k minus 1 plus n over k. And so basically what they did was since we know that this equals that, and they just plugged it in, found common denominator, and then proved it out. If y'all want to research that later, have fun with that. Okay, so in the triangle, like I said, there's a lot of different patterns. Like Trent was showing the Sierpinski's triangle. If you keep this going out and then highlight certain numbers, it'll show the Sierpinski's triangle. And there's also the pattern of 2. So like I said earlier, the top row is the 0th column or row. So if you take the sum of each column going across, and it's just 2 to the end. So 1 equals 2 to the 0th power is just 1. 1 plus 1 equals 2, and that's 2 to the first power. So that just keeps on going down. And then with that, there's also the magic 11s. So if you just look across them and just pretend that they're just read them as 121, that's 11 to the 2nd power. And if you keep on doing that, it'll keep on falling 11 to the nth power, 11 to the nth power. But when you get to the 5th row, you're like, okay, well that's not 11 to the 5th power. And that's because they're not counting for the place values of it. So if you account for the place values, you still get that, the triangle still continues on. So it's it doesn't give up at the 5th row, it keeps on going. Okay, that's it. Do y'all have any questions? No? Okay, cool.